All right, so this is going to be reviewing homework 6. We're going to do questions 3, 4, and 5. Let's just start off with question number 3 here. So we're recording. Okay. So here we have a helium neon laser. It's sent through that slit that's 0.3 millimeters wide, single slit. What is the width of the central maximum on the screen that is 1 meter from the slit? So we have like the distance L, right? That's how far it is from the slit. So this is a single slit dark type question. So then, the first question is what type of equation we're going to use. It's going to be that sine theta. So number 3, it's going to be that sine theta 1 is equal to m lambda over d, right? Where, d is like the width of the slit, that's the order number, that's the wavelength, and that's the angle we're going to experience. Okay, so in this case, we can just solve for theta 1 right off the bat because everything's given here. And so we're dealing with the first one, so 1. The wavelength is given, 632.8 nanometers. And then we know that distance, like the width of the slit, which is, what was it? 0.3 millimeters. Okay. So for the width, we could say, tan theta, like because we know what the how far away it is, right? We can say that tan theta 1 is going to be equal to y over 2L, right? And that's because there's 2 of them, right? And we can do the small angle approximation, which allows us to like interconvert that tan theta with that sine theta as such. And we can now plug in L, which, let me double check. What's L again? Oh, it's 1 meter. Okay. It's just 1. Okay. So now we can get an expression for what y is equal to. So from this, we can say y is going to be equal to 2 sine theta 1. All right. And we know what sine theta is. It's just this expression right here. Okay. So you can just replace this whole expression with that guy right there. And then you're going to solve for y, and y is going to end up to be equal to 0.00422 meters. Okay. That's like how wide it is away from it. So this one's actually pretty straightforward. All right, so number 4 now. Let's see. Number 4. So we have a beam of green light diffracted by a slit with that width. The diffraction pattern on the wall is that far away from the slit. The distance between the positions the positions of the zero intensity on both sides of the central bright fringe are 4.1 millimeters. Calculate the wavelength of the laser of light. Okay, so let me picture my notes here. So this is question number 4 now. Question number 4. All right, so the position of the first order maxima are going to be that like y over L, right? Like that's how we find where they are. And that's essentially equal to sine theta, right? All right, that's how we like it. How we find it. And what we can do is discern the spacing between those two, right? Because there's going to be it's like a wave, right? So it's going to be like a sideways wave, something like that, right? We can find the distance between these as delta y, where delta y is then equal to 2 times lambda d over L. Okay. So we now have enough to solve for lambda, right? We can now, or I mean, we're going to bring lambda to one side to solve for lambda. So lambda here is equal to delta y divided by 2, and then d over L, okay? And this whole thing comes out to be 547 nanometers. Okay, so you have to remember here, like this delta, what this delta y represents is the position of the zero intensity from both sides of that central dark, right? So there's going to be that central dark in the middle, and then we're going to have like both of them some distance away, which is represented by that central dark. And now that's what this wavelength represents, is what makes it such that like these conditions can be met, right? Okay, and now last one we're going to do, number 5, is number 5. Okay, sorry, I don't want to get chalk on my keyboard, so it takes me forever to scroll. So a screen is placed 5 centimeters from a single slit, which is illuminated with a 690 nanometer light. If the distance between the first and third minima in the diffraction pattern is 3.0 millimeters, what is the width of the slit? So we're solving for D now, right? And what kind of question is this? Is this constructive or destructive? Well, it's destructive, right? And that's because we're dealing with the dark fringe, right? The first dark fringe position. So because destructive, what's the equation we're going to use? We're going to use sine theta, which is equal to m lambda d. All right, and I'll say because single slit destructive, right? Sorry, destructive. Okay, so how does this look? It's gonna look something like this. Right, this is that distance, what is it, D. We're gonna have this guy over here, something like this. This is our center maximum right here. All right, CM, center maximum. And then this is our dark fringe, our first dark fringe. I'm gonna write DF, dark fringe, okay? So we know there's an angle theta between them. We know it's a distance L away, and we can call this Y, okay? So the first thing we need to do is, again, the small angle approximation. So tan theta, what is that equal to? That's equal to Ym over L. And then why do I say Ym? And that's because we're going to need to do this twice, right? We're going to need to recognize when m equals 3 and when m equals 1. Okay. And because theta in this case is like how, like due to like the all right, gotta slow down. Stop. Think about it. So because the length is so much greater than how that y value, we can use the small angle approximation, right? Because it's like essentially 0. Theta is like essentially 0. And because it's approximately 0, we can say sine theta is equal to tan theta, which is itself equal to Ym divided by L, okay? So that's because that angle is like approximately 0. So what can further be done is now replace this sine theta right here with this guy, right? We just showed it's equal to sine theta. So when we rearrange the equation, something like this, we'll say Ym divided by L is equal to m lambda over d. Okay. Where m, so I'm gonna write oops, spelled where wrong. Where m is gonna be equal to 3 and 1, right? So once I like do neat handwriting for a little bit, and then I'm like, oh, I'm doing it neat, confident, and then I just start being messy again, and then repeat. So m will be equal to 3 and 1. Okay, so what we need to solve for is delta y, where delta y will tell us that y3 minus y1 position, right? So when it will be at that third and that first, that's what that difference is going to tell us. So what does y3 represent? Well, that represents 3. So you're plugging in a 3 for m, lambda over d times L. Wait, I'm missing an L. Oh, yeah. So what you're going to do is you're going to bring this L to this side. Okay. And then minus, well, it's 1. So I'm just not going to, oh, that's right. 1 lambda dl. So this whole expression equals 2 lambda over dl. Gotcha? Gotcha. Okay. So what are we looking to solve is that d, right? We know we're going to plug in for y already, that delta y already. So we're going to rearrange the equation such that we have what will be d is equal to 2 times lambda L divided by delta y, and then solve for d. All right, and I'll leave the plugging in fun for you guys. Let me see if I'm totally in the way here. Move this down. Okay. Okay. So solve for D. That's the answer. Yeah, thanks for watching.